Concrete is the most widely used construction material in the world. It can be found in swaths of city pavements, bridges that span vast rivers, and the tallest skyscrapers on Earth. But this sturdy substance does have a weakness. It's prone to catastrophic cracking that costs tens of billions of dollars to repair each year. Concrete is a combination of coarse stone and sand particles, called aggregates, that mix with cement, a powdered blend of clay and limestone. When water gets added to this mix, the cement forms a paste and coats the aggregates, quickly hardening through a chemical reaction called hydration.
Concrete has one flaw, it's that it has low tensile strength, and therefore we need to add steel to make reinforced concrete. And in turn, the concrete needs to protect the steel from corrosion. I'm Kevin Payne, and I'm a Professor of Infrastructure Materials in the BRE Centre for Innovative Construction Materials here at the University of Bath.
My name is Susanne Gebhardt. I'm a Senior Lecturer in our Department of Biology and Biochemistry, and my day job is as a microbiologist, so I work with bacteria. And everybody understands that there is a crack in the concrete and the structure breaks, and then we can show them that it really works. So I find that
has a surprisingly short lifespan. After 20 to 30 years, natural processes like concrete shrinkage, excessive freezing and thawing, and heavy loads can trigger cracking. In this concrete, even small cracks can channel water, oxygen, and carbon dioxide that corrode the steel and lead to disastrous collapse.
Seal cracks as they form using bacteria which are able to produce limestone. Remarkable. And if we can incorporate those into the cracks or around the cracks that will form, the limestone will then plug those gaps.
Concrete is a very hostile environment, and the bacteria which fit the bill can survive in this hostile environment. The cracks in concrete are then impregnated with bacteria and bacterial food which has calcium, and these bacteria have used this calcium and carbon dioxide to precipitate calcite, and you can see that the crack is being healed by the bacteria.
Experimental blends of concrete include these bacterial or fungal spores alongside nutrients in their concrete mix, where they could lie dormant for hundreds of years. When cracks finally appear and water trickles into the concrete, the spores germinate, grow, and consume the nutrient soup that surrounds them, modifying their local environment to create the perfect conditions for calcium carbonate to grow. These crystals gradually fill the gaps, and after roughly 3 weeks, the hard-working microbes can completely repair cracks up to almost 1 millimeter wide. When the cracks seal, the bacteria or fungi will make spores and go dormant once more, ready to start a new cycle of self-healing when cracks form again.